Alright gang, here we go. This is Physics Unit 2 Part 5. We're going to be talking about Newton's second and third laws of motion. The video just previous to this, we talked about Newton's first law of motion, and we talked about force diagrams, free body diagrams, and force in general. Alright, so here we go. So let's just imagine we've got this situation where we've got some sort of launcher. Okay, so in class I used a rubber band. So we've got a launcher. It's got like a plunger on it, right? And we push that plunger down and we put a ball in front of it. Okay, so say we stick a tennis ball in front of it. So here's our tennis ball, and we shoot that guy forward, release the plunger, and it shoots that tennis ball forward with some acceleration, right? And then we take the same plunger, right? The same little launcher dude, the same plunger, right? But in this time we put a ping pong ball in there. Before it was a tennis ball and then a ping pong ball, and then we shoot that forward, and this guy got shot forward with a much bigger acceleration, right? And so we see by this, like, because our force is the same, but what's really different between the tennis ball and the ping pong ball is that they have different masses, that as our mass increases, our acceleration decreases, okay? As our mass increases, our acceleration decreases. So this is when we put a force on some sort of ball and our mass is increasing, then our acceleration on that ball has to decrease. So these two have what is an indirect or an inverse relationship. Okay. All right. What if we had instead we take one plunger that produces 7 newtons of force, okay? All right, and we put a tennis ball in front of it, tennis ball right there, and then we take another plunger that produces 10 newtons of force, okay? All right, and we put the tennis ball. Well, we know that because this guy produces has a higher number of force, the acceleration it produces on that tennis ball is going to be significantly higher, right? Maybe I should redraw this guy here, so that we have a smaller vector line. Okay, so it would be more like this. Okay, some sort of acceleration like that. All right, so anyway, so as our accelerations move from one to the next, right, we've got our different Newton force generators are going to produce a different acceleration. If we keep the mass the same, as our force increased, what happened to our acceleration? Well, our acceleration also increased. So that means these two have a direct relationship. All right, so that essentially just gets us right into Newton's second law. Okay, so this is Newton's second law, and it says pretty much that the acceleration of an object is directly proportional. Okay, acceleration of an object is directly proportional to the net force. Okay, and it's inversely proportional to the mass. Okay, all right, and really, so that's just a fancy way of saying this formula that I'm going to give you here in half a second. All right, so and these two examples pretty much walk you through what we just talked about. So if you increase the force, okay, it'll increase the acceleration. So we've got this 3 kilogram model airplane, and there's a 5 Newton force versus a 7 Newton force. All right, which one's going to have a greater acceleration? Well, 7 Newton forces, because you're launching it harder, right? In essence, one of the great laws of the universe is that if we increase force, we increase acceleration. All right, or the harder we throw things, the harder they go, right? Okay, increase the mass will decrease the acceleration. So if we have a 5 Newton force and we're putting on 2 model airplanes, one at 3 kilograms and one at 4 kilograms, which has a greater acceleration? Well, the 3 kilogram one is, right? What we just found was that the mass and the acceleration are inversely related. But if you really think about it, like you've got 5 newtons to throw something, you'll be able to throw the lighter thing farther than the heavier thing. All right? So really, this is where the rubber meets the road here. So everything we just talked about with Newton's second law, like all those words, this is really what it means, is that the net force is equal to the mass times the acceleration. Okay, so if we can find the net force and the mass, then we can find its acceleration. Or if we have the mass and its acceleration, we can find its net force, etc., right? So this means, remember, this is the Greek letter epsilon, and it means the sum of, S-U-M, okay? And so this is the sum of all the forces that are acting on whatever specific object that you're talking about. And we also refer to it as F net, right? And we talked about net force last time. Okay, and these last 2 bullet points are just about forces. All right, so let's do a practice problem here. So it says space shuttle astronauts experience accelerations of about 35 meters per second squared during takeoff. What force does a 75 kilogram astronaut experience during an acceleration of this magnitude? All right, well, we want force, and we know force is equal to mass times acceleration. All right, so our force has to equal our mass, which is in 75 kilograms. All right, 75 kilograms. And our acceleration is 35 meters per second squared. All right, so we can take 75 times 35, and we get 75 times 35, 12,625, but we only want 2 sig figs, so we'll say it's 2,600 newtons would be our units for force. All right, 2,600 newtons. Nailed it. Okay, so that's Newton's second law. Really, these in this class will essentially be pretty simple. All right. The one thing that might be kind of tricky is that, remember, this guy here, this is the net force. Okay, so sometimes if you're not finding the net force but you're using the force, then I might give you a problem where I give you several forces and you have to use vectors to find the net force first. Then you can plug that into F equals ma. All right, so always make sure you're using the net force. All right. Newton's third law says forces always exist in pairs. Now, if you think about it, if you're sitting down in a chair, okay, I'm sitting down in my office chair right now. I'm sitting down. My butt is pushing down on my chair, and the chair is pushing back up on me. If the chair wasn't pushing back up on me, then I just keep going through the chair until I hit the ground. Okay, yeah. Okay, so they always come in pairs. All right, and this is called an action pair or action-reaction pair. Okay. The action force and the reaction force. Now, this is a little bit of a misnomer. Like, it gives like the implication that something happens and then something else happens in response, right? There's an action and then there's a reaction. That's not quite how it works. They actually occur simultaneously. Both the action and the reaction happen at exactly the same time. It's not like a one then the other kind of situation. Okay, and so really we can just define it as whatever we want. Whichever one's the action, we define the other one's the reaction, but really there's no change between what we define as what. Okay, so here's Newton's third law, and this is a pretty verbose way of stating it. The real trick is this guy here. All right, for every action force, there is an equal and opposite reaction force. Now that's the kicker that you want to pay attention to. All right, so one thing to note is that the forces always act on different objects. Okay, and then because they always act on different objects, right? My butt is acting on the chair, and the chair is acting on my butt, right? And then what we were just talking about. But because they're acting on different objects, they don't cancel each other out. Okay, if I was able to, never mind. So just don't worry about it. They don't cancel each other out. Okay, and the motion. This is the other key. The motion of the object depends on the net force on that object. So if your net force is pushing you to the right, you're going to end up going to the right. All right. Okay, hammer on a nail. So there's a hammer. So let's think about the situation where we've got a hammer striking a nail on wood. Okay, so let's ignore this nail for a second, and I'm going to draw our own situation here. All right, so there's our nail. Okay, there's our nail. There's our wood. All right, and then we're going to draw our hammer. All right, so there's our hammer. All right, it's going to be a claw hammer because they're the best kind of hammers. All right, and then boom, and then this hammer has some sort of handle to it. Nice. So there's our hammer there. Okay, so let's think about what action-reaction pairs are going on. So we're going to choose different ink colors to help us keep track of what's going on. So so the hammer is acting on the nail, right? So we'll put this dot right here. Okay, and so with some force pushing down, okay, the hammer is acting on the nail, right? So we'll call this the force of the hammer on the nail. All right, there's one of them. Now the reaction pair of this, well, if the hammer is acting on the nail, then that means the nail has to be acting on the hammer, okay, and it's an equal and opposite force, right? That's Newton's third law. So equal in magnitude, opposite in direction, all right? So there's the force oops, shoot, dang. This could be a mess, isn't it? This is the force. This is the oh, I did it again. This is the force of the nail on the hammer. Okay, this is the force of the nail on the hammer. All right. So what else is going on? Well, we also know that the hammer, the nail is also acting on the wood, right? So let's see. Let's choose a nice, pretty. Oh, let's do orange. Okay. So we know that the wood and the nail are also interacting. So, all right. So the nail is acting on the hammer is acting on the wood. So it's like this. So this is the force of the nail on the wood. Okay. And then we also know that the wood is also acting on the nail. So off this point here that we've chosen before, we're going to draw another arrow, and that's that guy there. Oops, that's that guy there. And that's the force. Oh my goodness, I keep putting newtons for force. Force of the wood on the nail. Okay. Let's see what else we got. That's about it, right? The wood is also acting on the hammer, but only through the nail. So yeah, all right. And then we could also, if we really wanted to, we could talk about whoever's swinging this hammer. Maybe we'll do that on the next slide. All right. So let's see if we came up with the same ones. Force of hammer on the nail, force of the nail on hammer, force of the wood on nail, force of the nail on wood. Nailed it. Okay. So which of the reaction forces above act on the nail? Well, the only ones that are acting on the nail are the ones that start on the nail or have the nail in the second subscript. So it would be the force of the hammer on the nail and the force of the wood on the nail. All right. So these two here, these are our two that we care about. Now remember, so this guy here that we drew up here with the hammer and the wood and the nail, this is your force diagram. Okay, this is your force diagram. Now remember, the force diagram shows every single force, every single object that's going on in your space, and kind of gives it to you all at once without differentiating what's going on. Okay, since we're specifically asking about the nail, we draw what's called, remember, this is called a free body diagram. Where the heck did my pen go? There it is. So this is a free body diagram. All right, a free body diagram. All right. So the force of the hammer on the nail and the force of the wood on the nail. So then let's think about, well, what's going to happen to our nail? Is it going to move? Okay, well, we know we're hitting into the wood, so we'd better dang expect it to move, but let's look and see what our vectors say. So the force of the hammer on the nail, it goes down like this, and it goes down that far, and the force of the wood on the nail goes up, and it goes up that far. So we can see that the magnitude downwards is greater than the magnitude upwards, right? We can add these two vectors together, right, and just be like, all right, tip to tail, so it goes up that far, and then it comes down that far. And so our resultant would be from tail of the first to tip of the last. So the resultant would be from here, right, down to here. That would be the resultant vector. Okay, so we would have a downward vector. And really what it also says is that because the force of the hammer on the nail is greater than the force of the wood on nail, we're going to have a downward force. All right. So what forces act on the hammer? So let's just draw it. Since we've already got it started up here, let's talk about the forces that are acting on the hammer. Well, we've already talked about the force of the nail on the hammer. All right. Let's see. And then what else would be acting on it? Well, it's also, some sort of whoever's running the hammer, okay, is also going to be having, right, there's got to be some sort of hand here that's holding it. All right. There's my hand. Anyway, so we're going to have some last force here, okay? And this guy here is the force of the hand on the hammer, right? So the force of the nail on the hammer is also happening. The force of the hand on the hammer is also going on. And then what's happening? So we've got our hammer, right? So I'll just sketch this out again real quick. So we got our hammer, right? All right. I butchered my hammer. The last one was way better, I think. But anyway, it doesn't really matter. Yes, it does. Who am I talking to? Anyway, all right. So we had the force of the wood, the nail, and then we had the force of the hand. Okay. And so notice that the force of the nail on the hammer is much greater than the force of the hand on the hammer. Okay, so this really shows us, remember, when we're swinging our hammer, it's coming down. We're swinging our hammer, it's got a velocity in the negative direction that's going down. So we're swinging our hammer, it's going down. But once it starts hitting the nail, it's immediately going to start slowing down, right? Because it's transmitting its energy into the nail. It's going to start losing that energy, that kinetic energy. It's going to start slowing down. This is shown by our vectors because the vector representing the force of the nail on the hammer is bigger than our downward vector of the force of a hand on the hammer, right? So because this is going down slower or smaller, that we're going to start to lose our velocity, because that means the force is pointing up, so therefore our acceleration is pointing up, but our velocity vector is pointing down. And remember, when velocity and acceleration vectors are opposite one another, you start to get slow down. Right, so our hammer is going to come down. It's coming down fast, 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 and all of a sudden it starts to hit the hammer. It's going to start slowing down, right? Or start to hit the nail. It's going to start slowing down. Okay. Here's some action-reaction pairs. Okay, the desk pushing up on the book, right? My desk pushing up on my computer right now. Okay, and this my computer's pushing back down on the desk. Okay. Also, things pull up on the earth as well. The earth pulls down on things because of how massive it is, and the book is, and whatever object it's pulling down on is also pulling back up on the earth. Okay. Excuse me. So, so let's think about this real quick. So if we've got the earth pulling down on a book, okay, versus the book pulling up on the earth, what's the result of the action force? Okay, if that's the only force on the book. So we're thinking about, all right, our F net is the force pulling down. All right, so the idea is, so in order to get that, we get an unbalanced force, and it produces this acceleration. This is a terrible color. Remember, F equals ma, okay? So it's pulling down on the earth with some force, all right? And we can take the mass of the book, so the acceleration is going to be equal to the force of however hard the earth's pulling down over the mass of whatever it is. Okay, so because the book is relatively light, it gets a fair amount of acceleration pulling it down. But on the other hand, right, the acceleration is still equal to the same thing, force over mass, but the mass of the earth is pretty dang big, especially compared to a book. But so because it's so small, even though the force is just as big here as it is here, you get a much smaller acceleration because you're going to be dividing by a much, 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 much bigger number there. Okay, so that's it for part 5 of second and third laws of Newton. Do your practice problems, get ready for your labs and all that stuff. We got an exam just right around the corner, so keep on studying. Don't give up. Come see me if you need help.